Okay, hello everyone. Welcome to the ECE Colloquium. It gives me great pleasure to introduce one of our brilliant colleague, Professor Arka Majumdar. So Arka has been a assistant professor of electrical computer engineering and also physics at UW since 2014. So he received his bachelor's degree in Indian Institute of Technology in 2007. Then he headed to Stanford University, got his PhD in year 2012. After that, he went to UC Berkeley, did a short postdoc for 1 year. Then he decided to go to Intel Labs for another year before coming to UW. Okay? So since joining UW, he has done a great job and received many awards. He received the Air Force Office of Science Research Young Investigator Awards in 2015. At the same year, also Intel Early Career Faculty Award from Intel. Alfred Sloan Research Fellowship for Physics in 2018, and this year he received National Science Foundation Early Career Award. So without further ado, I'll pass the stage to Arka.
Thanks, Mo, and good morning, everyone. So today I'm going to talk about some of the work that we are doing on the field of dielectric metasurface over maybe like around last 4 years. It's a pretty new topic that we started. I started looking into it when I joined UW, and I'm going to tell you that how we think that it might be useful, or it has some technological applications in both in imaging and display technology. Okay, so let me first acknowledge my group who did it's not just they work on many other different things. I'm going to give you a little bit of overview of what other things we are doing as well. But this metasurface work is primarily done by Alan and Shane with help from some other students. We have a collaboration with inside UW, outside University of Washington. But this work, we actually did some work with Felix Heide in Princeton and also the funding agencies which funded many of this research that I'm going to present today. Okay. So before I go into details on the dielectric metasurface, let me tell you briefly about what we actually do in our lab. What is the kind of the basic science that we are studying. And the fundamental science that we're looking into is known as the so-called light-matter interaction, or we are trying to understand interaction between electron and photon at the nanometer length scale. And to do that, we fabricate various optical devices which has nanometer scale patterning, and that's why we call it nanophotonic structures. We make photonic crystal cavities, different kind of ring resonators, also dielectric metasurface. And then we integrate this nanophotonic structures with various different material systems, including 2D material, solution process material like quantum dots, perovskites, some complex oxide, also phase change material. Okay? So that's kind of what that's the technology we are developing. And with that, in our group, we are pursuing roughly 4 different research directions. In one of the research directions, we are trying to perform quantum many-body simulations with interacting photons. So we are trying to engineer interaction between light, and if the interaction is extremely strong and is present almost at a single photon level, you can study the quantum optical property of this light, and you can perform quantum many-body simulation. Now, this interaction between light also gives rise to strong nonlinearity, and we are trying to exploit that nonlinearity to create a system, a completely optical system that performs like a neural network. So you all know about deep neural network, which is gaining a lot of popularity nowadays, but it turns out that if you use optics, you can make it much faster, but one of the big bottlenecks is the nonlinearity, and we are trying to use this interaction between photon to implement that optical neural network. In collaboration with Intel, we are looking into some hybrid integrated photonics. Specifically, we are trying to integrate phase change material, this non-volatile material that we actually use in electronics as a phase change memory, and 2D material integrating with silicon and silicon nitride platform to really further the current status of optical interconnects for optical communication and also possibly for optical information processing. But the work that I'm going to present today is primarily falls under this nanophotonic computational image sensors. And we are trying to see how small sensors, how small imaging, imaging devices we can create using nanophotonic structures, for example, dielectric metasurface, and possibly some computational techniques. And that's what I'm going to focus primarily today. But if you have any questions about these other topics, I am here, so shoot me an email and we can chat and discuss more on that. Okay, so they mentioned that our motivation for looking into this dielectric metasurface has been making small sensors and small displays. Okay? The sensors or the camera has undergone a dramatic miniaturization. Okay? So it's maybe not as dramatic as Moore's law that we also show in our introductory slides in this ECE department, but you can see that the camera used to be very large, and now the camera that we are carrying all of us are carrying in our pocket is the volume is around 5 millimeter whole cube. Okay? But for the further applications, for example, for Internet of Things, machine vision, bioimaging, you probably need even smaller and smaller camera and smaller image sensor. And if you look at that, how do you reduce the size of this image sensor? It's not electronics anymore. It's really the way we do our imaging. It's the optics that limit the further miniaturization of this of this image sensors. And particularly what happens is the volume of a camera is fundamentally limited by a lens. You need to use a lens that has to be placed a focal length away from your sensor. So naively you may think, okay, we can reduce the focal length and we can reduce the volume, but generally we are relying on this kind of spherical structure. So we are relying on the lens that way that you guys know it. So if you want to make a short focal length, you need to make a fat lens, which kind of defeats the purpose of reducing the whole volume. Now, the other motivation has been that we all are living in this era of mixed reality. Okay, so virtual reality, augmented reality, it's everywhere. There are a lot of interest. One of the problem, it's not the only problem, but one of the important problem in augmented reality has been how do you reduce the size of the visor that you're wearing? So you need to create an efficient way of delivering light using an optical element from, let's say, a display. You reflect from a visor and comes to your eye. Okay? So both these two problems essentially requires miniaturization of optical elements, and we think that a very good solution can be this dielectric metasurface. Okay? So let me spend some time explaining what is dielectric metasurface. Now, if you ask this question, what is dielectric metasurface, you might get a different answer depending on whom you are asking. But for my research, we view dielectric metasurface as a sub-wavelength diffractive optics. Okay? So what is diffractive optics? So many of you probably already know, but just for the sake of completeness, let me explain a little bit that what we mean by diffractive optics. Okay. We all know from our high school physics that lens focuses light. That means your light that's incident, like all the rays that are parallel, hits the lens, but they bend and they focus at a single point. And the way we explain these things in our high school physics, that we have this surface, light incident at different part of this lens is going to see a different curvature, okay? And they are going to bend based on the principle of Snell's law, the refraction. So light is going to undergo refraction, but as they have different curvature, they are going to bend differently, and light is going to focus at a point. Okay? But now if we want to explain the same behavior using wave optics, we all know light is essentially a wave. The ray optics is a simplification. Then we can identify that light incident at different part of this lens is undergoing a different phase change. Okay? And the reason is they are going to undergo a different path length, travel a different path length, and that is going to give rise to a different phase, different phase shift depending on where the light is light is incident, and that actually also can give rise to bending of light that you can show from Fourier optics. But now that we understand that it's actually a phase shift that the light is getting, the wavefront is getting, we know the phase we always wrap to 0 to 2 pi. Anyone below 2 pi, we can make it map it into any number between 0 to 2 pi, and we can get our first diffractive optics. So anytime you can think about here that you are getting, let's say here the phase is 0, you go some amount and you get 2 pi, and then you wrap it to 0. Okay? So this is my first diffractive optics, but creating this kind of continuous profile using fabrication technology is difficult. So you can approximate this continuous profile, or you can think about you are quantizing this kind of signal, this kind of analog surface with some digital steps. Okay, so you can think about, okay, this is only one step. So in this case, we are giving some phase and 0, some phase and 0. That's one way to do it. Or you can start thinking about multiple different phase. So instead of like continuous profile, we are going to give multi-step, and we can get multiple phase difference. And how it looks like, it may not be very obvious to some of you that how actually the diffractive optics is going to look like. If you have a lens the height of the lens, in this case, this is the z-axis and this is the xy plane that's perpendicular to this, this projection plane, is proportional to x squared plus y squared. So you are going to see kind of a spherical geometry. But then when you go to diffraction or diffractive optics, you are going to do a modulo 2 pi, and this is how your structure is going to look like. Okay, so that's how like a diffractive lens look like. Okay, but now you have to do multi-level diffractive optics, and to do that you need different thickness. Okay, that's what we know, because light phase shift that light is going to get depends on how much light is traveling. And it turns out by nanofabrication, if you want to fabricate these structures, you need multi-stage of lithography. So if you want 16 phase shift or 16 different levels between 0 to 2 pi, you need to do 16 stage of lithography. Okay. Now what happens when you go to sub-wavelength scale is you can give different phase shift just by changing the lateral geometry. Okay? You don't have to change the thickness just by changing the lateral geometry of this element, so you can call it Nano Scatterer, you can give different phase shift. Okay? And that essentially gives you two benefits. First of all, you can fabricate that with only one stage of lithography, which is significantly simpler. And from very basic physics, you probably remember that if you look into the diffraction equation, you don't have any higher order diffraction when the grating periodicity, or basically the gap between different scatterers, becomes sub-wavelength. So that means you can guide all the light to zeroth order diffraction, which is a big problem in diffractive optics. So if you want to do diffractive optics, you will see light is going to lost in higher order diffraction, so it cannot be extremely efficient. But in this case, at least fundamentally, there is no efficiency limitations just coming from the higher order diffraction, because you can guide all the light to zeroth order diffraction. Okay? Now I'm going to spend some time explaining that why this thing actually works when you go to sub-wavelength, like what really changes. Okay? So previously, when I was saying that you need different thickness, I was relying on this fact that the phase shift that light is going to get is given by this expression, which is 2 pi over lambda. Lambda is the optical wavelength. N is the refractive index of the material, and L is the length that light travels. To give two different phase shift and the same material, everything is fixed, we have to change this L. Okay? That's our basic understanding of how it works. Now think about, you're taking this scatterer, you're making it very, very small, even smaller than wavelength. Then what happens? Okay? We know that light, when you do the ray optics picture, right, it comes to a single point. That's not exactly correct. So light has a special extent, and that extent is roughly around wavelength. So when it's reaching this really, really small scatterer, the light is actually seeing a medium that has some material with refractive index n and something that's air. So light is doing an averaging, okay, between this material that has refractive index n and the air that's refractive index 1. And that's how, by changing this lateral geometry, we are actually changing the effective refractive index, even when the key L is constant. Okay? Now, this is a very qualitative explanation, but it doesn't really give you the quantitatively how do you calculate, and it's pretty difficult. So you really have to solve full Maxwell's equation to figure out how much phase shift you are actually going to get when you have this kind of sub-wavelength scatterer. And that's exactly what we do. So use something that's known as rigorous coupled wave analysis. And what we can show here, that if you have, let's say, a cylindrical pillar. So we have cylindrical pillars arranged in a periodic lattice. And in this kind of structure, we have some thickness, some periodicity, and the pillar diameter. And just by changing the pillar diameter in this array, what we can say that we can give the phase shift from 0 to 2 pi while keeping the amplitude, the transmission amplitude, almost constant. So just by changing, in this case we wrote duty cycle, which is the diameter of this cylinder, we can give different phase shift. We are not changing the height. Okay? Now, we are using cylinder, but you can go crazy and you can come up with various different sub-wavelength scatterer structure. And this is actually some work from Professor Nanfang Yu from Columbia University. And it gives you a plethora of opportunities to be creative, come up with your scatterer design. You can simulate and see what kind of phase shift you can get. And it really brings diffractive optics to an extreme scale where you are doing this sub-wavelength engineering. And the reason it's possible today is because we have the fabrication technology of fabricating these structures. Okay? Just going to remind you, we're talking about SAR wavelength. So for visible wavelength, the SAR wavelength is less than 400 nanometer, or between, let's say, less than 600 nanometer. That's very small structures, which we could not fabricate, let's say, 20 years back. And these simulations that we are running, it's actually extremely computationally expensive simulation, but the computation is almost free today, so we can do that. And that's what makes metasurfaces a very, very important problem, because many of these Maxwell's were known. Maxwell's is an old problem, but the fact that we can fabricate the structures, we can design the structures using computation, that makes an excellent opportunity for us to look into this problem. Okay, so how do we design our metasurface? So as I mentioned, we start with a cylindrical like pillar. We use silicon nitride, and then we run many, many simulations with this rigorous coupled wave analysis. And in every plot, we have a fixed periodicity, fixed thickness, and then we are changing the diameter of the pillar. Okay? And we generate like many of these plots, and then we choose based on that which one is well behaved. When you say well behaved, that means are we getting phase from 0 to 2 pi? Are we getting almost uniform amplitude? Okay? And can we fabricate the structure? So these are the things that we kind of know from our experience, and that's how we choose our parameter. And we choose this one for most of our work. And this resonance that we are seeing, it's actually, there is a lot of interesting physics into it, and we are using some of this resonance to work with some of the atomically thin 2D material work, but I'm not going to discuss that today. But for metasurface, we actually neglect these resonances. Anytime there is a resonance, we are deep in transmission, we don't use that parameter. Okay, so once we know, once we identify scatterer geometry, the second thing is we need to identify what is the phase distribution that we are going to make. So for lens, we already know that there is a quadratic surface. I'm going to show you some other phase profile that we actually came up with intuition by literature study. And at the end of the talk, the second half of the talk, I'm going to tell you we can now even identify the phase distribution just using computation. So I'm going to explain that. But generally, we have to know what phase distribution we are going to make. Then we discretize this phase distribution in the XY plane. So each point in XY point, we have a phase shift that we need to give. So we go in this plot, this is the phase shift we need. We go here, we find out what duty cycle or diameter we need, and are going to place that scatterer at that XY location. Okay? Now in doing that, we make a very interesting approximation. It's called local phase approximation, which essentially is telling that a whole periodic structure behave like a single unit cell. Okay? And this is strictly not valid, but it works fairly well for metasurfaces that we have seen from our experience. And there are like, I'm going to show you like there may be some new design principle we can adopt to not even make that local phase approximation. But it actually makes our life somewhat simpler. So when you fabricate this structure and design, this is how it looks like. So you can see the scatterers, the size is changing, lateral size, and each of the scatterer gives me some phase shift in that XY location. Interestingly, you can see we started to make a cylinder, okay, and we get something that doesn't look like a cylinder. And it still works really well. And that's another thing that what metasurface is so popular is one of the criticism of nanophotonic structures has been it's extremely difficult to fabricate. It's very sensitive to fabrication. But it turns out in metasurface, even though you have a lot of scatterer, like your fabrication may not be completely perfect, it still works very well. And the reason is the field is distributed over the whole metasurface. So if you have a small problems in some scatterers, that doesn't really affect the overall performance, which is not the case for various nanophotonic structures, for example, waveguide or optical resonators that we all are working with, and we know that fabrication is extremely important for that. Okay, so the metasurface is no way a new field. Okay, even though this term was coined maybe in last 5-6 years, this work started by in 1998. People were looking into this kind of sub-wavelength grating structures to create optical elements. But in recent years, almost fueled by actually plasmonic metasurface, which we are not really going to talk about today. I'm doing primarily dielectric metasurface. But a plasmonic metasurface, this feels somewhat rejuvenated, and there are a lot of work that has been done, as you can see, in recent years. We actually use silicon nitride to make our metasurface. And we use silicon nitride because this is the material that you can fabricate today using a CMOS-compatible foundry. So CMOS-compatible, The CMOS compatible foundry essentially means that the foundry that is making your computer chips today, we can use the same kind of fabrication facility to fabricate this metasurface. And secondly, silicon nitride has very wide band gap, so you can make visible frequency metasurface. So when we first fabricated this metasurface lens, you can see the Nano Scatterer. This is how the lens is focusing. And we'd like to point out here, the silicon nitride till date is the smallest refractive index that people have used to create metasurface. Okay, so its refractive index is actually pretty small. It's n equal to 2, whereas mostly people work with silicon whose refractive index is 3.5. And we have recently figured out that there is actually some penalty you pay when you go to low refractive index, but almost all practical applications, it works fairly well. Okay? So not just lens, we can now be more creative. We can start making this element that create a light with an orbital angular momentum. And just to kind of give you an idea that how small these lenses we are making, this is an example of a conventional lens that we use in our lab, and this is like my student is holding, so you can see the hand. Now, there's also a glass slide, and if you zoom very closely here, you can see there are 7 dots. And each of these dots is a lens. And if you focus on this dot, this is what you're going to see, that there is a very, very small nano scatterer that we are making. So we can make extremely small lenses using this technology. This lens can have like 10 to 20 micron focal length, so very short focal length. And more importantly, we can be really creative and create different kind of phase profile. And as I said, we have not really done anything on the scatterer geometry, but that's kind of another avenue that we are currently pursuing to see, can we even extend the capability of these metasurfaces. Okay. So going beyond lens, we started looking into something that we call freeform optics. So freeform optics is that if you come up with a phase profile that's not rotationally symmetric, that's actually extremely difficult to fabricate using the conventional diamond turning technology. So we demonstrated something known as Alvarez lens, and I'm going to point out, explain it a little bit more because I'm going to bring it back later in the talk. So what this Alvarez lens concept is that you use 2 cubic elements, okay? So you're not using a lens, and as I mentioned before, lens actually require a quadratic phase profile, kind of a spherical phase profile. You use 2 cubic elements. They look something like this. 1 cubic element is this, the other one is exactly opposite of that, okay? But then if you laterally shift them, what you are doing mathematically, you are doing actually a derivative of this cubic phase profile, and you get something that looks like a lens, like profile, like a quadratic profile. But interestingly, that you can see that this circle size are changing. That essentially means your focal lengths are changing. So by laterally tuning these elements, we can change their focal length. And interestingly, you can see by changing only micron scale displacement, we can get millimeter scale displacement in the focal length. And tunable focal length lens is actually very useful for machine vision and many other applications. Just to show you that we actually fabricated this structure, this research was published in this journal. You can see this is how the cubic profile look like. This is the Nano Scatterer. This work that we did back in like 2017, we did it by manual changing. So we put these 2 lateral on the stages. We manually changed it. Recently, in collaboration with Professor Carl Boringer in University of Washington, we started integrating MEMS actuators to change this metasurface. And as I mentioned, we need to change only like 10 to 20 micron to give like almost millimeter scale or even centimeter scale focal length change. MEMS can't do that. So that's something that we are working on, and we had moderate success in actuating these metasurfaces using MEMS. Now, all these structures that I was showing is small, fabricated with E-beam lithography, which some of you probably know is very expensive, extremely low throughput. So we developed a stepper photolithography process where we can actually start making these metasurfaces in the wafer scale. Pretty large area, you can see, it's almost 1 centimeter by 1 centimeter. But if you zoom into it, you are going to see this nanoscale scatterer there. We also demonstrated imaging with this tunable focal length. So you can see there you have a zoom imaging of Mona Lisa here. This is the Air Force pattern. We can tune the focal length, and we can do varifocal imaging using this large area metasurfaces. And also, kind of for fun, we started looking into can we make a lens using other material. And another material that we actually study in our lab is atomically thin 2D material. So this actually lens we fabricated by patterning hexagonal boron nitride. So we create small scatterers, and we get a lens. And what we showed here hopefully it will be visible in the screen, is even when you cannot get the whole 0 to 2 pi phase shift, we can still create a very efficient lens, and by following some design principle that we developed in this paper. And this one is supposed to be the most brightest. That's what we saw as an experiment, that we designed it to be the best, given you don't have the whole 0 to 2 pi phase shift. Okay. Okay. So with this background, I'm going to talk about 3 different projects. Okay, where I'm going to show you that using some computational technique, how can we improve these metasurfaces further. Okay, so first thing I'm going to talk about is full color imaging with computational imaging, and then some inverse design of metasurface, and then I'll change the gear a little bit and tell you this is primarily a design and theory work at this stage, that how can we make a near-eye visor using metasurfaces. Okay, so let's talk about the first one. So far I told you metasurface is all wonderful, everything is good, but of course there is a catch, right? And the catch is it has very strong chromatic aberration. And this is nothing to do with metasurface, that's how diffractive optics work. Okay? Diffractive optics is known to have extremely strong chromatic aberration. That essentially means your color quality is extremely poor, and you can just get black and white imaging. And what happens in this case, this is actually experimentally measured result for RGB, for silicon nitride metasurface. The green gets focused in one point, red gets focused another plane, and blue gets focused another plane. This is along the optical axis. So you have a lens, we are measuring along the optical axis, and they get focused at different points. Okay? So if you, let's say, place a sensor here, green will be very well focused, red and blue will be extremely badly focused, and you are not going to capture those information. If you have seen the flip phone, if you have used flip phone back in like 2003, 2004, when the phone camera first came out, that's what this image quality is going to look like. You see all the colors kind of separated, looks like rainbow. Okay? So people actually have looked into this problem. Professor Andre Ferron, who actually also gave a talk in Colloquium, I think last year, and Professor Federico Capasso from Harvard, they started looking into some unit cell engineering, and it's called, the technical term is called dispersion engineering. That instead of a one scatterer, can you actually now play with the scatterer in the unit cell and at least make a lens that work in two different wavelengths. And they had very, very good success, that they actually can make a lens that work on 2 wavelengths, not broadband. But then they extended this technique very recently to show that you can actually have the full visible frequency operation. So you can do full color imaging using this dispersion engineering. This 2 work came out earlier last year in Nature Nanotechnology. It was pretty impressive that it can be done. But so these are the material they use, but one of the problem was these are polarization sensitive. So this scatterer, as you can see, this is how the scatterer looks like. These are not rotationally symmetric, so depending on whether you're sending X polarization or Y polarization, they are going to behave differently. That's not how your cell phone camera works, because all the light that we are capturing is actually unpolarized light, and if you use the polarized this metasurface, you're going to throw away half of the light, which is not very good. The second thing is, it showed that it cannot be applied to large area. So you can make only maybe a 30 micron meta lens, the 30 micron diameter, so it's extremely small, where you basically correct for colors, you basically correct all the scatterers, but it cannot be applied to a larger area. Now, larger area is important. I mentioned that metasurface can reduce the focal length, but you need large area to collect more light. Like that's actually a fundamental problem in optics in some way, that if you make a small aperture, you are going to collect less amount of light. There is no way you can change it. So you really need a large area lenses, maybe not like very large, but at least 1 to 2 millimeter lenses for actually practical applications. So we wanted to solve this problem using a different way. And our plan was that if you image with a conventional metasurface lens, that's how image is going to look like, because you have chromatic aberration. Okay? How about we actually don't use meta lens, we use another optical element, okay? And we distort all the colors, but in a predictable way. We know exactly how we are distorting our color, and then can we actually do post-processing to get back the full color. So that was our idea, that we are going to design an optical element that's going to distort all the colors, but we know exactly what it is doing, so we're going to do some deconvolution at the end to get back our image. So when we are coming from primarily like nanophotonics kind of device community, so we looked into literature and we found this field computational imaging. And it turns out they already have solved this problem. Back in the days, it's called wavefront coding. Okay? And the idea was that we have a lens, and we add an extra cubic phase mask. So they use two optical elements, a lens and a cubic phase mask, and they get a range of uniform point spread function. Okay? So what it means in this case, point spread function, you can think about is like focal, when you have a focal plane, that's like a point, that's like a point spread function. Now they have this cubic element actually gives you something that looks very similar along the optical axis. So what it means that if you have a lens, traditional lens, in the focal plane, it looks very nice focusing. You go a little bit away from the focus, you see blurry, and that's why you have chromatic aberration. When you do this cubic element, you see something that doesn't really look like a lens, but it remains almost same over a long length along the optical axis. And if you are doing optics for some time, you probably already have recognized this is this ARA beam that we are creating. So when you send it to a cubic phase mask, we're going to create an ARA accelerating beam, which is diffraction free. So that people knew from before. And back in the days, they also actually tried to use this kind of cubic phase mask to solve chromatic aberration, but for refractive optics. So refractive optics also has chromatic aberrations, but that effect of that is actually much, much smaller than what we have in diffractive optics. So we wanted to solve that diffractive optics problem or metasurface chromatic aberration using this technique. So the first thing we realized is we don't need to put two optical elements. We are in the sub-wavelength scale. We can actually add these two phase shift and create only one surface. Okay? And if you are working in optics lab, you'll know that aligning two optics is significantly difficult than aligning only one optics. Okay? So you can reduce the number of optics. And we came up with this phase profile that's given by this expression. So this, the first part is for the lens. It's actually a hyperbolic lens. And then we add a cubic term to it. Okay? So when alpha is equal to 0, we just get the hyperbolic term. That's what it looks like. So this is what I showed you before, that how the diffractive optics looks like. But these are not continuous. If you actually zoom in, you will see this nano scatterer. This is an optical microscope image. But when you put alpha, you will see the effect of this alpha, this rotational asymmetry that's coming. And by changing alpha, you can actually extend the depth of focus more, or you can improve the imaging quality depending on what kind of alpha you chose. Okay? So what is the effect of the alpha? So if your alpha is equal to 0, that's like an ordinary lens. Along the optical axis, that's what it looks like, which you already have seen. So this is actually done for red, green, and blue. For these three different colors, they are going to focus at different spots. Okay? But now, if we do that for with alpha is equal to 92 pi, we are going to get a very elongated kind of focusing effect, even though they don't look like focus. Okay? But they have information content in one plane. So we can put a sensor in one plane where all RGB actually has some information content. Okay? So this is theoretical result. So we did the experiment, and we put the sensor, and we measured the field profile. So alpha equal to 0 at the sensor plane. Green looks well focused. This is how blue and red looks like. They looks pretty blurry and big. But when you put it with the cubic element, alpha equal to 92 pi, this is what we get. So they look very similar. Okay? And they have like information content, okay, in all the scheme. So let me explain what I mean by information content is because after that we calculated something that known as modulation transfer function, okay? And modulation transfer function is very similar to the transfer function that we talk about in maybe control system, but essentially it's telling you how much of the spatial frequency, this is not temporal frequency, how much of the spatial frequency of the scene actually get captured by your optical element into the sensor plane, okay? So if you calculate that MTF from this PSF, so you take a Fourier transform of the point spread function to get this MTF, we find for green, for large number of normalized spatial frequency, it's capturing all the information. But this is where the problem becomes important for this kind of blurry. You get a lot of zeros here. Zeros are bad because zeros you cannot invert. So zeros essentially means you are not capturing any information on those spatial frequency, and that's why if you have a blurry image, you cannot like completely recover the image without some prior knowledge. With prior knowledge, you can do that, but without any prior knowledge, you cannot get back this image because you are not capturing those information. But with our cubic profile, you are actually going to see something like this. So you can see all of them looks very similar, plus they have a pretty large non-zero component for different very high normalized spatial frequency. And that's what enables us to do computational reconstruction of the image. Okay? So we went ahead and fabricated the structure, and in this case, we fabricated a 100 micron diameter metasurface, and the separation between metasurface and sensor is 200 micron. Okay, so just to kind of give you an idea, your hair thickness is 100 microns. We have a 200 micron focal length lens, and we measured under this blue, red, green, and blue LEDs. So I'm just going to focus on only one of this Mona Lisa one. So you can see if you do the meta lens, so in this case, basically quadratic profile, the usual metasurface lens, green is very well focused, well resolved, but blue and red looks very blurry. Okay? When you use our element, they all looks uniformly kind of bad, but they look very similar. And then when we use the computation, you get back this image. All the Mona Lisa are kind of in focus. So we can also quantify that how good it is by something known as structural similarity, that how similar these images are. The highest value of structural similarity can be 1. For meta lens, we get 0.7. Our approach, we get 0.9. It actually depends on the actual what you are imaging. So depending on some imaging, you might not see big difference. You may see higher difference depending on what kind of image what kind of scene you are imaging. And just to show you, tell you that the computational algorithm that we are using is called Wiener deconvolution. And complexity is order n log n. N is the number of pixels. Okay? And this is a textbook method, and there are now a lot more better algorithms that we are actually exploring right now. So this is done with the 3 LEDs, but in your cell phone, you are actually doing a white light imaging and using a colored camera. So we wanted to try that. So in this case, we did a white light image. And then we use a colored camera, and this is how it looks like. So these are the original images that we wanted to measure, and this is for Singlet, is essentially a meta lens. This is what the EDOF stands for extended depth of focus lens. So this is the cubic element. So what we captured, and this is after your deconvolution. So I can just maybe focus on this one. So this is the tulip. You can see the sky color is not visible. The stems gets blurry. We get back this color, and we can also get the stems looking very good. Okay. And one thing we wanted to point out, this is not done for just RGB. This is actually done for all the wavelengths. That's why we did also a rainbow imaging. So that definitely the color quality is better with our method. Okay? We extended this thing to actually get very focal zoom imaging while maintaining the color. And we use this idea of the Alvarez lens, the cubic element that we are laterally sliding to get a lens-like behavior with this colored, kind of the wavefront coding approach. And we came up with a quadric metasurface. So now the phase that we are implementing has an x to the power 4 terms. Okay? And this is how it looks like. So we also fabricated and tested. I'm just going to very briefly talk about. So you can see this, there is an extended depth of focus that you are getting when you are laterally sliding them. And by laterally sliding them, you can change kind of this brightest spot is shifting. This is how it looks like. And we also did some imaging with that. So ground truth is this bird. The Singlet meta lens is pretty illegible. When you do the captured, it's like you can probably see that there is a zoom going on, but when you deconvolve, you start seeing the zoom better, and you can also see the color. And just to kind of show you here in one of the image, this is how the Singlet meta lens look like. Definitely you can start seeing the colors like the feather and the beak here. But now still the imaging quality is pretty poor. Okay? And that's something that we are currently working on. So the first thing you need to appreciate that this is done with a 100 micron diameter lens. Okay? So that means you are at least collecting 100 times less number of photons. So your signal to noise ratio is supposed to be 100 times less. That's just pure physics. That we cannot really solve. The whole point is that if you make a refractive lens, which is 100 micron size, can you still preserve this kind of color information? So that's the right way to think about it. But of course, we are now looking into kind of, can we do increased lens aperture to improve the image quality? There are a lot of computational imaging algorithms that's specifically designed for low light imaging. So can we use some of those techniques? We have not done anything on the geometric aberrations here. So we can solve this geometric aberration either using computation or using two metasurface that are some of the work that came out from the metasurface community. And also you can see there's some streaking going on, and that's coming from the fact that our PSF is rotationally asymmetric. So we have developed some rotationally symmetric EDOF lens that we have designed. Now we're going to test and see how it looks like. But why do we want to go from here? So I started with saying that we want to make small image sensor. But just small is not good enough. So if you look into the actual problem, we need small size, but we also need small power. Okay? We don't kind of spend too much power in the reconstruction. So if you use a lens-based imaging, that kind of your cell phone camera, your size is large, but your power is almost zero. And in this case, we are talking about the reconstruction power. I'm not talking about the sensor power, because that you always need to capture the information, but there is no reconstruction power. Now, there's another paradigm in computational imaging that's known as lensless imaging. Okay? And lensless imaging essentially tells you that we put some random medium in front of this detector, and we know exactly what it is doing, and then we can reconstruct the image. But that complexity is almost order n cube, where n is number of pixels, which is actually extremely power consuming. And a lot of people have, actually there's a company called Rambus Labs, they tried to kind of commercialize it for smart home applications, but it did not really work because the power consumption was too high. Our approach falls somewhere here. We still need to place it a focal length away, but our focal length can be small using metasurface. But we lose something, like we lose the color information, but we can get back with the computation, but our computational complexity is order n log n. Okay, so it's much lower. And we want to go somewhere here, and it's not quite clear what that is. Okay? So while thinking about it, we realized that what we are actually doing with the metasurface is something that you can think about optical information processing with metasurface or metaphotonic element. Okay? We are kind of load balancing the computational load both into the optics and the software. Okay? So let me kind of explain like what I mean by that. So let's say you want to, this is your object. It can be a landscape or it can be a face. And what you want from your sensor is either exactly faithful reproduction of what the scene was, or you want to make a decision. Is it a human? Yes or no? Okay? You want to just maybe make a decision. So we can think about, okay, we are going to make not a single metasurface, a stack of metasurface that's going to give me maybe the outline. I mean, this is, I'm just saying that this is possible. Or we can get like some color information which is uniformly distorted, but that's not what we want. So then we can do some post-processing using a software to get to this location. Okay? But in this case, this post-processing work, we're not solely relying on post-processing. We are actually doing some sort of computation using this kind of metasurface, and these are all linear computation. So we are not bringing nonlinearity, which remains a big problem for optical computing. Now, how do you design this metasurface or stack of metasurface? That's an open problem. Can you use computational design of metasurfaces? And more importantly, can we now design this metasurface and these two together? Okay? Can we do co-optimize the meta elements and computational imaging algorithms together to get the best possible performance in terms of power and size? To solve this one, we recently developed actually a TensorFlow-based end-to-end optimization code. So we actually show like what actually optical image formation happening using metasurface. We have a model for that. Then we do the noise corruption with the deconvolution, and then we put different image, what image we want, and we actually find out that what is the best metasurface geometry, what is the best deconvolution software, and just to show you some simulation result. So if you have an initial metasurface, this is what it looks like. So if you zoom into it, you cannot see what is the boat number. Then we actually do some deconvolution that we came up with our intuition, like linear deconvolution. It looks better, but you still cannot read it. But then when you do the final version, that's after the TensorFlow optimization, we can start seeing this writing. So this is actually something that we are now going to fabricate and test. But we still don't know how to design this metasurface, right? How actually going to design this metasurface if we don't know what, like if it's not a lens, let's say. And that brings me to the second part of the talk, this inverse design of metasurface. Okay? So let me explain what it means. There are two inverse problems in metasurface community that people are facing today. One of the problem is, given an application, how do you identify the desired phase distribution? The cubic, like lens, quadric, that we all came with intuition. But I can tell you a problem, and I'm going to give you an example, that you have no idea what is the phase distribution. How do you do that? Okay? And secondly, given a phase distribution, how do you identify the correct distribution of pillars? Okay? So I told you about local phase approximation. That's like, of course, is an approximation. But why cylinder? Why not anything else? How do you identify that? So these are the two kind of problems that we are solving. And we developed some techniques to kind of solve both of them partially. There are, of course, a lot of room for improvement. And the idea was we are going to use computer to tell that, okay, what is the optical element? So we'll start with some initial conditions, some initial value of the scatterer. We run the simulation. We calculate a figure of merit. So for example, for a lens, we can say that put all the light in this point. Okay? Then you do the inverse problem, so you do adjoint optimization. This is some of the methods that actually people used in fluid dynamics for a long time, and now people are also using in nanophotonics. Is we calculate the gradient, and then we update the scatterers, okay? So the first thing we wanted to see, like, okay, does it really work? And also, I forgot to mention, this forward problem to solving the whole Maxwell's equation is extremely expensive. So it generally takes, for a whole metasurface, it takes like 20 minutes. So you cannot really run this optimization when one step takes 20 minutes. So we came up with this idea for like using Mie theory to calculate this metasurface, but that limits us to the scatterer shapes. So currently our Mie theory works only for spherical scatterer or ellipsoid scatterer. So this is what we first designed. So in this case, we designed a lens. We say put all the light here, and we started with an element that has uniform radius of the spheres, and we get back this rotationally symmetric structure. Okay, these are all theory. So we thought about, okay, lens we already know. Can we do something more than that? So we asked this problem to do something called point function engineering, which is useful for depth sensing for microscopy. Is can we actually create an optical element that doesn't focus light in one plane, but it focuses light in different XY position along the optical axis. So it's basically created helical beam. Can we actually do that? Okay. Now here your intuition is not going to work very well. So that, okay, what is that element that you're going to focus light in one point in XY plane, in next point in different XY plane? So it looks kind of something like this. So we said, okay, let's do our inverse design. And that's when we realized that coming up with the figure of merit is actually non-trivial. And one of the big criticism of this inverse design has been that we are just solely relying on computation. So what is our knowledge going to come? Like, we study about optics, we have some intuition. What is the role of intuition? And I believe this is where the role of intuition is, that how do you actually come up with figure of merit? Just to give you some example, we first thought about having this the yellow part is a bright spot, just those spot as our figure of merit. It doesn't work. Actually, you just see that the light is basically remains focused in all those points, because that's where the figure of merit gets minimum. So you have to kind of restrict the figure of merit. And we came up with this idea that we put like two dark spots, and these two dark spots are the spot. So you have to basically put some penalty in this figure of merit. So these are like the neighboring bright spots actually becomes dark in that plane. So this is how we came up with this figure of merit. And we put it in our software, and this is what comes out. It spits out this kind of spheres. And I would like to point out this is probably the highest area optical element that has anyone designed with inverse design. So previously, what people have done is probably 1 micron or maybe like 5 micron whole square. This is 150 micron whole square, and that can be done because we are using Mie theory. There is no way you can do 150 micron whole square using electromagnetic inverse design, like solely Maxwell inverse design. But of course, there is a penalty I'm going to talk about it, that we have just spherical shape. So this is how our simulation look like. So the light is actually going to focus at different spot. You can see, if you look closely, you can probably see this dark spot. This dark spot that we try to kind of make in the neighboring plane. So this XY location is here, and we want to make it dark spot, and this is along the optical axis. Now we want to test it, but it works only for sphere, right? We have only sphere. How do you fabricate sphere? Sphere you cannot do with e-beam lithography. So we used 3D printing. And in like 2-3 years back, through a grant with another faculty in mechanical engineering, we secured an optical 3D printer that has a resolution of 200 nanometer. So we use that to create the structure. This is how the structure looks like. If you zoom into it, this is this Nano Scatterer. These are actually sphere. So it's not completely sphere. You cannot really make a sphere because your contact angle is kind of, there is like no contact spot. The sphere is going to fly off. So it's like almost 90% sphere, and then we have a flat base. And it works fairly well. We are pretty impressed by that. You can see this brighter spot here. This is actually changing, and this is an experiment. This is done with 1550 nanometer. This is because we need a somewhat larger structure to use nanoscribe. And if you see this brightest spot here, they match fairly well. So this is there's a simulation, there's a red spot, they fall into a circle. So basically, we're putting the XY location for different plane, and our experiment matches fairly well. Okay? But of course, there is we need better computational method to accommodate arbitrary shape of scatterer. That problem is not solved. So we're looking into some multi-scale inverse design, where we probably will do like we'll solve Maxwell's in unit cell, and then take that to create this larger area, maybe using Mie scattering or some other theory. And also, figure of merit engineering is non-trivial. And that's why I think it is extremely unlikely we can come up with one inverse design software that's going to solve everything. We need input from engineers to figure out what figure of merit we need. And actually, I was talking to someone who works with Boeing a lot in mechanical engineering. They call it objective function. So some of you may be more aware of that term, but it's the same thing. Okay. So in the last maybe few minutes, I'm going to change the gear, talk about some design of this metaform near-eye visor, so no longer in sensing, more in the display technology. So we are living in this era of mixed reality, like virtual reality, augmented reality, why it is not a reality, like why actually it doesn't exist today. One of the big problems, there are many problems. There are a lot of problems that actually doesn't involve optics, but one of the problems is the sizes are very large. Okay? Now, if you look into the optics of these devices, there are fundamentally two different principles that people are using. One is a reflection. So they use light. The light gets reflected from a visor, come to your eye. And you can show very easily, as you bring this reflector close to your eyes, your field of view is going to be limited. And the reason is, when you're using reflection, your incident reflection angle is same as incident angle. That's how like reflection works. So you cannot bend light with any arbitrary angle. The other approach has been a grating-based approach where you have a waveguide, and the grating is kind of, you can think about like another diffractive optics. But here, you are changing the light by almost 90 degrees. It's a pretty inefficient process, so you lose a lot of the light. Okay? So we wanted to actually combine reflective and grating structures. We have a reflector, but on the top of reflector, we are going to create this nano scatterer to bend light larger than what reflection allows, but probably not by like 90 degrees that this grating is trying to do. Okay? And that's essentially what our metasurface is. So we proposed this idea back in 2017 that within 2.5 centimeter away from the eye, we can create a flat metasurface. So we don't need to have this bulky form, and it actually works fairly well. So just a little bit of the design approach. So we start with a ray optics software, ZMAX, and we came up with this phase profile that gives you this large angle that you can, like essentially when you have 25 millimeter or 2.5 centimeter away from your eye, and that's the number we kind of roughly came up with, like what your sunglass is away from your eyeball. You can still basically have large field of view. We calculate the modulation transfer function and compare it with what exists today. I'm not going to smart details, but this is actually comparable with what currently most of the AR visors actually provide. One of the problem in AR, for virtual reality is fine, but AR we have to have see-through quality. So we have this metasurface in front of your eye that everything is reflecting light to your light from display to your eye, that's fine. The virtual world looks fine, but your real world has to come through that metasurface, and it's going to look very distorted. So we realized that we can actually solve it by using another metasurface, and this metasurface is 100% transmissive. So when the light comes in, this metasurface pre-distorts the light, which gets distorted again by this another metasurface, and they together, actually, they don't have any wavefront error. And we also optimize using ray optics software to get this phase profile. And we have another way to actually take this ray optics phase profile and simulate in the electromagnetics to make sure that actually it works. Because these ones are 2 centimeter by 2 centimeter big element that we are optimizing that we really cannot do using electromagnetics. So how the metasurface will be designed, so this is actually, we are looking into this silicon nitride scatterer on some oxide silicon nitride, like partially reflective distributed bag reflector. You don't want 100% reflective because then your see-through quality will be very bad. And then we have another metasurface here, and we design them. So basically right now, you can see that the reflection of this metasurface is around 40%. So 40% of the light that comes from here will go to your eye. But when you are sending light from here, you want it to be 100% transmissive. So you have a very large transmission efficiency. So we actually have these designs done, and it took like quite a while because there are a lot of small things that we had to figure out when you go for this kind of ray optics devices. So final performance that we have, if you see this HoloLens one, and this blue one is Magic Leap, and the green one is kind of our visor, we have a significantly larger field of view. And we also have very good see-through quality. So current visor, the wavefront error is 1.17 lambda. You want it to be as small as possible. And with our visor, it's actually 0.63 lambda. So definitely, metasurface allows us to get large field of view, also good see-through quality. But of course, there is some problems. So one of the problems is the chromatic aberration still remains a problem, especially for the reflective light. So when you have the see-through light, the two metasurfaces are kind of canceling each other. That effect is not that bad when you're looking at the real world. But for the virtual world, it may be a problem, and this it boils down to what is the application. For industrial scale, you can just have a single color, black and white, and that's completely fine. But if you're looking for consumer application, that needs to be solved. The fabrication is difficult, non-trivial, but it can be doable. People already have done this kind of fabrications. We are looking into that. And we have not solved this problem that I'm not going to go into details, this Virgin accommodation conflict, but there are idea of solving that using tunable lens, and we want to use this Alvarez lens with this visor to make ultimately actually something that looks pretty small and works pretty well. Okay, so I'm going to summarize. I told you about some of the work on the full color imaging that is possible by co-optimizing metasurface and a computational algorithm. But we need better computational imaging algorithms that we're looking into. This co-optimization actually is a very interesting idea that we got pretty excited. We are working with Princeton on that. Inverse electromagnetic design, we think we are just scratching the surface. So this is a very new idea, and I think there are a lot of opportunity of using better computational technique to create like optical elements that doesn't even exist. We don't even know what they are. And I told you about the kind of chromatic aberration. So I think kind of what I want to end it with is the metasurface is not necessarily a very new thing. Many people actually even call it like an old wine in a new bottle. You just put a new name. We already knew about it. But I think there is a tremendous opportunity for improving metasurface for two reasons. One is we have extremely sophisticated fabrication technique today. And secondly, our computation is almost free. It's not free, it still requires a lot of computation. And that gives us a lot of opportunity to look into some of this old problem that people already have looked into but could not solve. And we think there is a lot of opportunity to improving sensor and display and probably even like optical computing. So thank you.
We have time for a few questions from the audience. Yes.
That was a great talk. Thank you. On the first topic, if you use the extended depth of focus, the field, and does that give you some advantages in manufacturing, placing the lens and have a lot more tolerance from the lens to the sensor in manufacturing, or does the computation vary upon the axial distance?
So the question is, when you use the EDOF, do you actually have more tolerance between the gap between the lens and the sensor? And the answer is absolutely yes. We just need to know what is the gap once you make it, because ultimately when you are doing this deconvolution, we need to know what is the point spread function. So if you don't know what is the gap, like ultimately when you placed it, if we can measure the gap, or we can probably do some calibration for different PSA. But yes, I think like we actually have seen that one of the projects that we are trying to do is bringing anything at focus. So the gap actually has some leniency. That's true.
Any other questions? I have one. So
yeah.
I've read many proposals proposing using machine learning to do the inverse design.
Yeah.
What's your view on that?
So I think we have to be very careful on what we are designing. So I have to say this. So far, I have not made anything, or I have not seen anything where inverse design performs better than forward design or better than intuitive design. But if your intuition fails, and it's actually very easy to fail here, not that much in integrated photonics, like, okay, you want to bend light in different angle, but here, or different frequency, go to different path, but here we can come up with problems which are extremely non-intuitive. And there, inverse design provide a solution. It's surely not the most optimal solution. But having said that, I think there are a lot of computational technique that we can use to solve this problem. Like in fact, like I think this whole passive computing, that there might be this machine learning. And we are not actually using machine learning. We're using adjoint optimization. So that's fall under like some kind of convex problem. And you can show this problem is non-convex. That's why we are getting into local minima. But we have to be very careful saying like what is the actual power of inverse design. I think you need intuition to also, yeah.
Anything else? Any other questions? If not, yes.
Yeah, so your computational imaging algorithm I'm in the embedded emphasis in undergrad here, and we talk a lot about getting things into an FPGA in acceleration, to get it done quick and solved by parallelism. And have you stepped into that, or is this done when you compute? How is it line coding?
So you are saying like whether we have looked into the computational to have like an FPGA or something. So we have not, but we actually, I recently developed a capstone project for a few undergrad who are developing that to put it into FPGA. So that definitely actually something that we think that there's an opportunity of improving the computational parts. We are coming from very device focus group. So once we reach that, it kind of works. We don't look into systems that much, but there is a lot of opportunity of really looking into this computation also into FPGA. And that's what you need to do if you ultimately make a system. You cannot use large computation in your laptop. But this is something that we are actually exploring with some undergrad student, not in the main research area.
No, I think that holds a lot of promise. So my other question is, you had this variable focus length with these cubics that you were moving. Were you actually moving them, or were they?
No, we are actually moving them. So that's
you move just like a micrometer.
Yes. Okay. So that we can do with the MEMS. So when you do it by hand, we actually buy really expensive computer control stages, which is maybe $2,000, and then we change it a little bit. But with MEMS, actually it's actually easier. You can do micron scale, and you have to, the total range can be difficult. So total range is 20 micron. But yes, we are physically moving them. Yeah. And the physical moving is not the scary. Your cell phone, actually, these things are physically moving. This lens that you have, they move. So when you bring something very close and it gets blurry, and the lenses are actually moving in your cell phone as well. So
we're in the sensors and sensor systems class, so there's a lot of some overlap.
Yeah. So.
Okay, a lot of interesting discussions. Then we should end and thank Arka again.